Okay, picture this. A robot turns on for the first time in a building it's never seen before. To do anything useful, to even move without crashing, it has to build a map. But here's the catch. How do you store a super detailed map of a huge space without completely running out of memory? Well, it turns out robotics has a really elegant solution to this. And today, we're going to dive into the clever data structure that tames this memory monster, the QuadTree. So yeah, this is the big question, right? How does a robot actually map a totally unknown world? It's not just about snapping a picture. It's about building a genuine understanding, a memory, of a brand new place. This is one of the absolute core challenges in robotics. And the answer, as you'll see, is a really smart mix of sensors and some clever data tricks.
Now, your first thought, and it's a totally logical one, might be to just create a giant piece of digital graph paper. Just fill in the squares as the robot sees things. Super simple, very direct, but this super intuitive idea has a massive resource-hogging flaw hiding just under the surface.
To see what I mean, let's think about a warehouse, maybe 100 by 100 meters. If our robot wants to map that space with just 1 centimeter precision, how many tiny little squares does it need to keep track of? The answer is 100 million. That is an absolutely colossal amount of data for a little computer on wheels.
And that, right there, is what we call the 100 million cell problem. It's the brute force way of doing things, and it is just wildly inefficient. Why? Because most of that space is just empty floor or solid wall. You just don't need that much detail for huge, boring areas.
And this image, this side-by-side, makes the difference totally obvious. Look at the standard grid on the left. It's so wasteful. It has to store info for every single one of those 256 cells, even the big, empty white ones. But the QuadTree on the right, it's smart, it's adaptive. It uses these huge cells for the empty space and only breaks them down into smaller pieces right where it matters, around the edges of that object. And this is where your jaw kinda drops. That standard grid needs 256 cells to store the shape. The QuadTree, it does the exact same job with just 49. That's an 80% reduction in memory. We're talking about the difference between a map that would totally cripple your robot and one that's incredibly lightweight and fast.
So, how in the world does the QuadTree pull off this incredible trick? Honestly, the best way to think about it is as a map that can zoom in and out all by itself. It knows to add all this high-res detail, but only where things get interesting. And the source material for this explainer uses the perfect analogy. It says, think about Google Maps. When you're looking at the whole country, you don't need to see every single house number, right? You only need that fine-grained detail when you zoom way in on a single street. A QuadTree does that exact same thing for a robot's world. Okay, so we get the why, it's all about efficiency. Now let's get into the nitty-gritty how. We're going to break down the actual mechanics of what makes a QuadTree tick, splitting and merging its building blocks, which are called nodes.
At its heart, the definition is actually really simple. A QuadTree is just a way of taking a square of space and, if it needs to, chopping it up into 4 equal smaller squares, or quadrants. And it can keep doing that over and over for each new little quadrant. Quad means 4. It's right there in the name.
And here's the basic anatomy. Every square you see on the map is a node. Now, if a node is all one thing, like it's all empty or it's all a wall, we call it a leaf node. It's the end of that branch. But if a node has a mix of stuff in it, say half empty and half wall, it becomes an internal node. And its job is to split into 4 smaller child nodes to capture all that new detail.
And these 2 operations are the magic that makes the whole system work. You have splitting and combining. When a robot finds a new obstacle in what it thought was a big empty room, the node for that room splits to add detail. But on the flip side, if a robot explores 4 little squares right next to each other and finds out they're all empty, they combine back into their parent node. This cleans up the map and saves a ton of memory.
So how does the robot actually feed information into this system? Well, it uses sensors, like a LiDAR for instance, that shoot out beams of light. The path that beam takes through the open air gets marked as unoccupied, and then the exact spot where the beam finally hits something, that gets marked as occupied. This whole process is called array update, and it's how the real world gets translated into the language of the map.
Okay, enough theory. Let's put this all into practice and make it super concrete. We're going to follow a little robot, we'll call him Pip, as he uses a QuadTree to map out a room for the very first time, step by step.
So, Pip starts out in a completely unknown room. The map is just one big, gray, unknown square. Then, Pip sends out his very first sensor beam. and bam, it hits a wall. The QuadTree just springs to life. That one big node immediately splits into 4 smaller ones, adding all this new detail to show that the path the beam took is free space and the point it hit is a wall. The other parts, they're still unknown for now.
Now watch what happens next. As Pip keeps exploring, it scans a new area and discovers it's totally empty. The QuadTree is smart enough to see that 4 adjacent cells are now all the same. They're all unoccupied. So it triggers that combine operation. Poof, they merge back into one bigger node, instantly simplifying the map and freeing up memory.
So what we just saw with PEP shows that this isn't some static, pre-made map. It's a living, breathing representation of the world that literally adapts as the robot learns more. And this process is what gives us smarter maps, which in turn gives us much, much smarter robots. And if we were to peek under the hood at the code, this is the basic logic you'd see. You'd have a central function, ray update, that's kind of like the boss. It takes in all that sensor data. When it gets new info that doesn't match the current map, it calls the split function to add more detail. And when it confirms that an area is all the same, it calls combine to save memory. It's this constant back and forth that keeps the map perfectly balanced.
And after all that splitting and combining, this is the beautiful final result. This is what the world looks like through the eyes of a QuadTree. Just look at it. All the tiny little squares, the high-resolution stuff, it's all clustered right around the edges between free space and occupied space. The big, wide-open areas, they're represented by big, efficient blocks. It is a perfect, memory-saving picture of the world.
So let's just boil this all down. The 3 big takeaways. First, efficiency. QuadTrees are amazing because they don't waste memory on big, boring, uniform areas. Second, adaptability. They give you that super high resolution, but only exactly where you need it. And third, they're dynamic. The map isn't set in stone. It grows, it shrinks, it evolves right alongside the robot as it explores.
You know, this kind of technology is absolutely fundamental for any kind of autonomous navigation. We're talking everything from warehouse bots to search and rescue drones, maybe even rovers on other planets. Which leaves us with a really exciting question to think about. With maps that can literally learn and adapt on the fly with this kind of efficiency, what new frontiers is this going to unlock? Where will robots go next?